I was rushing real fast here at the end to finish up some stuff that I'm doing for work, and I got that all wrapped up now, so time to get back to doing what we're doing. You can see I have an empty screen. Let's keep it like that for a moment and just kind of catch up. So what we've been working on so far is the N puzzle problem, and we've been doing just the 8 puzzle problem in particular, which is a 3x3 board missing one tile for a blank that you use to slide around and adjust all of the different tiles into their different locations. What we found yesterday is that it is a much more difficult problem to solve optimally than we originally thought. What problems we ran into are first off, that breadth first search uses an enormous amount of resources for this problem, this really kind of simple problem, and that just crashed basically when we ramped up to the hardest problem. The hardest 8 puzzle problem takes 31 moves to solve. And what we found was that in order for us to actually explore all of these moves, on average, we had 2.66 branching factor. And I want to say we did this to the 30th because there are 31 moves that you have to make. And this turns out to be quite a large number. Divide by 1024. That's millions, that's billions, that's trillions. Yeah, so we would have to search through like 5 trillion different, states total in order to solve this board. And that's kind of a crappy way to go about it, because if we look at the total number of states that you can reach, it's just 9 factorial in this case, which is... Oh, 9 factorial. That's 99 factorial. 9 factorial. So there's really only 63,000 states. So we somehow turned looking and evaluating 360,000 states into evaluating 5 trillion states. So no wonder breadth first search was not a very good solution for this problem. Today we're going to do a couple of things. First off, we're going to start by sort of taking advantage. Oh, well, I guess we should recap the rest of what we did yesterday. So then we switched over from breadth first search to A star search, and we had talked intermediately about greedy first, which is normally your next step. Unfortunately, because all of the step costs in this problem are the same, meaning that each time you move a tile, we add 1 to the total cost. There's not some variable cost for each action that we take. What happens is your greedy first search just reduces down to breadth first search, and that was no better than we already had. So that's not good. This time, we're going to do a few things. I've got a to-do list, which was on my blog, and let's just go ahead and take a look at it. If you're not aware, I have a blog. And each day after the stream, that's cultureofdevelopment.com, and each day after the stream, I post a little recap of the stream. And I'm really starting to like the idea of putting a couple of like to-dos for like what you can expect the next time around. And I made a list of to-dos for today based on sort of some of the problems that we ran into last time. First off, I want to redefine the goal state. So I went back and I was reading through the literature, and the way that we had defined the goal state is that the blank is in the top left-hand corner and the highest number is in the bottom right-hand corner. And reading back at the literature, the 1 is in the top left-hand corner and the blank is in the bottom right-hand corner is the way that you come up with 31 moves for the hardest solution. So what we're going to do is first off redefine the goal state. After that, we're going to move on to some performance tooling. So we ran into this problem last time where like it was taking a long time and it was using a ton of memory, but the reality is we weren't really sure what kinds of like how much work it was actually doing. So this time we just want to put a couple of like little counters in there, and we want to put a little like pulsing like log basically that says, like, say, I don't know, every 10 seconds or so, oh, I've done this much work in the last 10 seconds, or I've done this much work total, just so that we can kind of have an idea about you know, what it's doing, how fast it's moving, et cetera, et cetera. So we can see that if things slow down once it gets further into the search, or you know, just whatever is going on. Just something to output also, so that we're not looking at like a blank screen and watching the performance monitor on my, you know, the task manager, because that wasn't really that fun. All right, so we're going to do a little bit of performance tooling, and then after that we're going to improve the nodes explored per second by orders of magnitude. All right, so I put this on here. The reason that this is going to turn out to be kind of slow, and we're going to see this once we have this, is that our state right now is actually eating up quite a bit of space. Let me go ahead and bring this up. Search problems. Oh yeah, I got rid of it. I merged it in with the fast, since it's all part of the same project. You can also find this on GitHub, on my GitHub, which is at github.com/Nick Larson. And if you go here, you will see, where are my repositories? You will see fast. This is it. This is what we're working on. This is the matrix multiplication project, and this is the search problems project. So here's a link that you can go to, github.com/Nick Larson/fast. And you can follow along with this, send me pull requests, whatever you think is interesting. For the stream, I'm pretty much going to stay on the same path, but by all means, I will merge in and I'll just branch off for each different stream. I want your updates. I want to be able to get through this. Solving this problem is much more important than like running a stream to me, because it's just, you know, it's interesting and it's fun and it's hard, and that's what it's about. You know, doing something bigger than just me, hopefully. Okay, so that's where you can find the code if you want to follow along. All right, now the actual way that we are storing this stuff is in search problems, and it's in InPuzzle. Okay, in InPuzzle, like we have this integer and we have this byte array. So right now this is 3, this is a 3 by 3, so this is 9 bytes. And then this is 4 bytes and 4 bytes and 4 bytes. So we have 4 bytes, 8 bytes, 12 bytes, and 21 bytes total for this entire representation. And we're also going through, and right here we have a byte array, which is an allocation that is not part of this class itself. And because of that, when we do the copy of this thing, it actually takes quite a bit of work. And so what we're going to do to increase the speed by orders of magnitude, my assumption at least, is we're going to reduce this entire state down to only a few bytes. And hopefully all of the operations that we want to do on this state are just modifying a couple of bytes, and that's it. And hopefully we basically reduce, you know, the copy operation down to copying an integer or copying a long, you know, effectively the same thing. And so that's how we're going to go about doing this. All right, let's see what else we had on the list for today. All right. Next, we want to actually implement the Manhattan distance metric. So last time we implemented the Hamming distance, and the Hamming distance, just to remind everybody, is the number of misplaced tiles. Again, let's take a look at, you know, in puzzle, let's call it 8puzzle. 8puzzle problem. I don't want one of these. 8puzzle images. There we go. This is the 8puzzle problem, again, where you just sort of slide the tiles around and there's a blank, and you can move the 6 into the blank, the 4 into the blank, or the 8 into the blank, and then the blank moves to wherever you moved that to. And the goal is to rearrange them all so that they're like this, only instead of it being like this, we're going to put the one here. We're gonna do it more like this. This is what we're gonna consider the goal state, instead of considering this the goal state, which is what we currently had. So this is the one that's used in the literature a lot more, and this is what we want to stick to so that when we start comparing our results to the literature, we'll get the same sort of numbers. Oh, there's a little bit of an illusion going on, like an optical illusion. When I look at this, I see dots in each one of these little blank spaces, and it's really bugging me out. Do y'all see that? That's crazy. That's really crazy. Okay. Anyway, back to the point. And then after that, we want to actually solve the 8 puzzle today. That would be great. The hardest problem for the 8 puzzle. That way it feels like we're making progress. It's Friday. We can all go home. We can feel great. Or, you know, just go upstairs if you work in your basement like I do. All right. Sorry. That's it. If you have any questions, please feel free to ask. I am happy to answer. I would love this to be more of a conversation than me just talking into the void constantly. Also, thanks for joining. All right, let's get started. So, number 1, we'll just go down the list. Number 1 is redefine the goal state to match what's common in the literature. Perfect. So this is the goal state is the isGoal function. IsGoal. And right now we expect it to be a 1 in the first place. And then we expect the blank to be at the very end. So let's see. Expected come on. All right, so what we're going to do is we're going to say expected equals expected return false, and then we're going to update expected. We're going to say expected equals plus plus expected mod. Plus plus right here is just instead of a post increment operator, which returns the value and then updates the value, meaning that it returns the value and then whatever operations you do happen on the original value, and then the actual value at this location of this variable is updated for later on. Instead, what this does is it updates the value and then uses it. This, I think it's called a pre-increment, post-increment versus pre-increment. Yeah, okay. Yeah, there we go. There are a few nuances to this. If you are new to software development or just language stuff in general, you probably want to read this. You'll see that I end up using these sorts of things quite a bit. In .NET, at least, when you do something like, let's see here, when you do something like expected plus plus versus expected equals 1, these are two totally separate operations in the way that they compile down in both what you call it, in both I am losing my mind. The way that they compile down into machine code, where they actually get executed, this turns out to be a single machine code operation. This has to actually load the 1 into a register, and then it has to perform the add operation on that. And at one point, maybe we'll compile this and we'll go and take a look at it. And what you'll end up seeing is that these don't have the same runtime, and you can actually test this in a tight loop pretty easily, where this one turns out to be a lot faster than this one. This is one of those things where it's like in Python, I want to say like there is no plus plus operator, and so you end up seeing expected plus equals 1 all the time, and I want to say that it's gonna end up compiling down, like it's just a case that they look for. That's certainly not the case in .NET. So you'll end up seeing me write these plus plus post increment and pre increment quite a bit because they're just a little bit faster. Okay, so now what we want to do is we want to say expected equals plus plus expected remainder of this dot in. Let's say, okay, private int total cells equals, okay, and then we want to update this here. And then we want to say this dot total cells equals n times n. This is going to be useful because this n times n is something we end up looking at quite a bit. Let's go down here. This dot total cells. Okay, so this is saying increment the expected and then take the remainder divided by the total number of cells. Since we start at 1, this has the effect of counting all the way up to the number of cells. So on a 3 by 3, it will count to 9, or rather, it will count to 8, and we'll look for 8, and we'll increment it to 9, and then we will take the remainder of dividing it by 9. That's what this operator is. This is the remainder operator in .NET, not the mod operator. And what this will end up doing is dropping it back to 0 for the last one that we're looking for. And again, we'll just test this real fast before we go too much further. Let's see, when I do the copy now, I added a new value, which increases the size of the state even more. I just need to make sure that I'm actually copying it. So total cells equals this dot total cells, and anywhere else I need to do it? Shuffle in puzzle. This in, that will take care of it. This is us doing private initialization, which is copying it somewhere else. This is really a kind of an anti-pattern to do. This sort of an anti-pattern because there is no initialization. Have to check everywhere every time we update. Okay. Excuse me. All right. So that ought to do it. Let's go check the is goal, and we'll do that in the program. Shrink this down so it doesn't get in our way. In puzzle. Oh, that's another thing. We need to change the initialization so that it's in the goal state. What do you mean there's no definition for in puzzle? It compiles. Seems like it's right here. CD space search problems .NET restore .NET build. Okay. Well, whatever. Initialization now needs to be the same sort of a thing. Shuffle, initialize. Okay. So int value equals 1. Equals byte of value, and then I wonder if we can do it with a byte. Yeah, all right, cool. value equals plus plus value mod this dot. Oh, there is no this. Okay, total cells. Int total cells equals size times size. This is total cells. Okay, so we got the same idea here. We have now initialized it instead of being the old goal state to being the new goal state. And we are checking whether it is the goal. So now what we want to do is bring back the goal check. We're just going to add this as a function. Private static void. Okay, check test goal initialization. Okay, and what we're going to do is copy this. You know what, we're going to say test solve. Private static void test solve. Alright, and then we also have test goal initialization. Okay. So now what we want is console.writeLine of puzzle3. And then we want console.writeLine of puzzle3.isGoal. And what we're checking for here is that it looks correct and that it is marking it as a goal. And then we want puzzle3 dot, we want to shuffle it, and we want to shuffle it one time to guarantee that it is no longer a goal state, and then we want to write out again console.writeLine of just a divider, and let's see if that works. .NET run. Build failed. Man. Alright. Come on. Cannot implicitly convert int to type on in puzzle 53? 53. What? Oh, I'm on program 53. In puzzle 53. Okay. Let's try it like that. Okay, so we see now that we have 1, 2, 3, 4, 5, 6, 7, 8, 0, and we do count that as the goal state correctly. And then we have, that's not right. Oh, you know why? Because we didn't change, and see, this is one of those things where it's like you got to test both, because we didn't change the initialization of the blank row and blank call. So that was just a mistake. And this is going to be n minus 1 and n minus 1. That was really wild. Is there anywhere else that we set those? Nope. Let's try that one more time. All right, this is still correct. And then we have now that the 6 and the 0 switched places. Okay, so we're good. Let's try it just one more time to see if we can get the switch with the 8. And it switched with the 8. Okay, so we're good now. All right, and that is it for the first thing on the to-do list. Let me just copy these and make an actual to-do list out of them. Bloop. And increase the size of this so we can all see it. Now we're just going to have to-do stream Put in a divider. I like my dividers if you can't tell. And now we're going to have done divider. Redefine the goal to match what's common in the literature. Great. Add some performance tooling, counters for explored nodes, and a regular pulsing of performance info. Yes, let's do that. Okay. That is going to be basically part of the solver. And right now, I think we're using the breadth first solver. So let's go ahead and let's just check that real fast. Puzzle. All right, we have tested the goal initialization. Now we're looking at the solve. The solve initializes the puzzle to the hardest puzzle. We don't even need the shuffle anymore. Puzzle 3 hard. We are using breadth first search solver. Why is there no definition? Why can I not F12 today? I'm just going to restart this and see if we can make this work. Have you ever tried turning it off and turning it back on again? That was one of the questions on the Stack Overflow developer survey. That makes me laugh. Can I F12 now? No, I cannot. What's going on? I've got C# installed. I don't know. I'm not really sure. If anybody has any ideas about why I can't F12 today, that would really make my day, because this is going to get really old. Go to implementation? What is F12 even doing? No definition found. Shift F12? No results. I don't know how to fix this. If anybody has any ideas, please drop me a line. That would be super helpful. Okay. We have made some changes here to actually do one of our things, so let's go ahead and check it in. Let's say not fix. Change goal state to match literature. And this is on 8 in puzzle. All right. Okay. Now we are trying to go to the breadth first search solver. Great. And basically what we want to do is we want to count all of the expansions. So that's what we want. We want a public. Great. We want a public long, because, you know, trillion doesn't exactly fit in an int, assuming we could actually go that far and wait that long. Long states public long states evaluated get set. All right, now basically what we want to do is just increment this every time we pull something off of the queue. So we have pulled this thing off of the queue, and we're going to say states evaluated plus plus. There we go. So that will add a little bit of performance checking. Now let's go ahead and throw some output on here as we're going through it on the program. So as the solver, now what we want to do is figure out a way to occasionally inspect this. Now we want to figure out a way to occasionally inspect this and print out the value as it is going. Okay. So There's a lot of ways to go about this, and I'm going to choose what I think is just an interesting way that I've never tried before, which is we're going to create the solve as an async method so that we can return a task from it. Then we're going to loop, checking to see if it is solved. Maybe we just set a timer instead. You know what? Let's just set a timer. Timers are easier. So, reporting timer. Reporting timer equals new timer. And we're going to have to go look up the definition for this. I always forget where these are. C# timer system.timers. So that everybody can see here. Let's make this a bit wider. All right, what we want to do is create a timer system.timers, and yeah, I guess dot elapsed. Okay, let's just copy all of this actually here because it looks exactly like what we want. Okay, so let's call a function when the timer goes. And so let's just say, nope, didn't want that. We need to add an, yeah, I guess we'll just copy this, whatever. Okay. No, we want this. We want to create the thing that we want, which is right here. Okay. Now we have var solve. No, reporting timer is a new timer, and we want it to give us some information, say every 10 seconds. Are those milliseconds? We should check that. Timers. Timer every 2 seconds is 2000 milliseconds. Okay, great. So we're going to do every 10 seconds we want something to happen, and this elapsed system.timers using system.timers, and then hopefully this gives us some actual info. Okay, great. Elapsed. Oh, come on. Oh, I changed the name of it. Duh. Let's give some attribution to the place that we found this, which is right here. Although this is a Microsoft URL with a framework ID, so this URL is certain to break. Okay. Just leave that in there anyway. Elapsed is an elapsed event handler. Guess we're gonna have to look that one up. Elapsed event handler. Elapsed event handler takes an object sender and an elapsed event args E. Okay. Seems reasonable. So basically I want a delegate that takes an object and this. And what I want to do is console.writeLine of states evaluated plus solver dot states evaluated. Auto reset, reporting timer enabled, true. Sure, this timer up here though I want to start after we set up all this stuff. right before we call the solution. Okay, so we're going to do that. And now I don't have access to the timer, which is a little frustrating. So let's go ahead and do something like, it'd be really nice if what I want access to is the timer so that I can write out the amount of time that has passed and the number of states that are evaluated. But I guess for the time being, we're just going to do it sort of like this. And I'm going to add in a function here called log, called private static void log. And this is basically going to do the same thing, string value, only we're going to append a timestamp. So we're going to say console.log.writeLine, writeLine of datetime.now dot to string yeah, we'll just let it do it however it wants to do it for now. And then we're going to say colon, I guess we'll even do it like this. There we go. Plus value. And now we're going to say log of this instead. Okay. So when we run this, we want to turn this off, reporting timer.enabled right here. Reporting timer.enabled equals false. And you know what? We can actually do this. Because we don't have to start new. We can just have it be new stopwatch. Like that. And then we can have it be timer.start. And then down here, reporting timer.enabled equals false. Okay. So now we want to drop this down to the next line because we're going to add a little bit more here, which is plus, and I guess at this point it's getting a little long-winded. So we'll do it like this and just have it be 1. This is string interpolation, if anybody's not familiar with this. It's in a lot of languages, so I don't know. States evaluated. And I think for states evaluated, we want to show it at a constant width so that the timer always shows up the same width. So solver.states evaluated. And this is going to be like in, I don't know, 20? How many was trillion? No, 15. Let's try 15. And then here we're going to have time. We'll say milliseconds. Millis. And this is going to be timer.elapsed dot total milliseconds. And I want to not just say dot total of milliseconds on a timer because or not elapsed milliseconds, because you'll notice it's a long and you don't get partials on this. And once we get to things that are faster, I'm going to care about the partial milliseconds. So for now, we're just going to go ahead and get it set up for that later on. Okay. I think this is going to be good. Again, later on we'll change the formatting of this, but for now I think this is just going to be fine. And let's see if this works. CD space search problems. So we know that this is not going to finish. The goal here is just to see that we're getting the pulsing output and to get a bead on roughly how many states per second are being evaluated. Excuse me. Search problems. .NET run. This is in development mode. Oh no, puzzle 3 does not exist in the current context. Program 60. Program 60. Yeah. Puzzle 3. Okay. You know what? Let's go back. Let's have this be var puzzle equals puzzle 3. This might sound silly. We just want to have it so that later on when we want to try other ones, we don't have to change this. We only change this. I don't want to get rid of this and then forget about it or have like a bunch of comments. So things we can worry about later. Puzzle. If you're new here and just showed up, welcome. Please drop a line in the chat. Say hi. If you have any questions about what's going on, feel free to ask. I have plenty of time to answer all of your questions. We're just hanging out on a Friday, really, so, you know, ask anything. Doesn't really have to be related to whatever. Now I want to change everything called Puzzle 3 to just Puzzle. And now, cross our fingers. Yay, the build failed. It only failed one time this time on 36. Puzzle 3 hard, that's why. Okay. Hello, world. Give me a pulse. We have to wait 10 seconds. Maybe we have to wait 10 seconds? Hey, what's up? Alright, okay, so let's change the formatting of this to be a little bit better because all those zeros are kind of silly. Let's see here. C# format long. Formatting long variable as string. Long. I don't want it like that. Set width. Format long. Set width. Yeah, fixed spaces. That's what I'm talking about. Format string. Why did that make it hard? Format. -20? Is it -20? I tried your solution. It does not work. Let's see here. Somebody has sent me a message. Yay. Okay, I was not super interested in that. Okay. String goes here. Text 1 is value 20. Can I do how to format long fixed width? Fixed width? To be 010. I don't want pad left. To string. D3. Okay. Format. C# format strings. Standard numeric format strings. C. D is a decimal. E, fixed point. G is a general number. N is an integral and decimal digits. So maybe what I want, P, number multiplied by 100. R, result. That can round trip to an identical number. X, a hexadecimal string. Where is the one that's just an integer? I just want an integer to come out. D6. No. Kind of silly. I don't know how to do this. How about we just do something really hackish, because I don't care to waste a bunch of time on this. And instead of putting this, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's try that. All right. And when you're doing testing like this, you don't wait 10 seconds. You just drop it back to 1 second so you can get your answer as quickly as possible. Okay, that appears to have not done it. Okay. C. So we're just gonna have it be print out the number. I don't know. You know what? I'm not gonna worry about it for now. It's not super important. I think the only thing I do want to change is make it easier to read. Pound, comma, 0. Like this. Commas are always a little bit easier to read. Yeah, there we go. Okay, so this is doing like 500,000 states per second right now, which seems like a lot. Well, first off, let's go cross off our list. We have done what we wanted to do. We have a regular pulsing output of some statistics about what is going on. So yeah, let's cross that off our list. Add some performance tooling, counters for explored node, regular pulsing of performance info. Great. Let's go. Add performance pulse. Okay. Now, let's go to the next one. The next one is improve the nodes explored per second by orders of magnitude. All right, so this is what I was talking about where, yeah, we're doing 500,000 a second, and that might seem like a lot, but this game is so simple, and this board is so small, there's no reason we shouldn't be doing, like, literally tens of millions per second. So going from 500,000 and just arbitrarily here, well, I guess we should run it in, you know, release mode before we get all crazy about saying how fast it's running. And now we are going to wait 10 seconds, but it's going to give us a nice, like, a nice number to look at. And you know what? Just going to do it. I'm going to add one more to the output here. This looks like, yeah, still 500,000 states per second. Like, that's just not good. It doesn't matter whether we're in debug mode or not. It's just slow. So what we're going to do here is kill this. We're going to put an explicit thing in here that tells us exactly how much. And now we're going to have this be like this so that we can put a timer in here. That doesn't work, does it? That would be way too easy. Void. Why is this complaining exactly? Oh, yeah. Inside of here, you gotta have this. Okay. And what we want to do is say var states per second equals solver dot states evaluated divided by timer dot elapsed dot total seconds. And this is going to give us a measure in states per second. Okay. States per second is states per second. All right, one more time. Let's take a look at it, and we'll just drop it back to 1 so that we can see it. And now we won't have to like do math. We can just look at the number again. Okay, stop this. Let's put commas. Okay. Oh, nope. Come on. Dot? I don't know. Did that do it? Great. Okay, well, we're just gonna... This is just hacky. We're just gonna stick with it. We're just gonna keep rolling with it. Kind of got what we wanted. Want a little bit more precision, although it doesn't seem to matter. So we're doing... You can see that, like, it sort of juggles around a little bit. It's not super duper consistent. But the idea is the same, that we just get a straight number that we can now compare to each other. And so let's add this back in. Report states per second as well. Okay, so now our goal is to increase that number dramatically. The reason we want to increase this number dramatically is that we're going to see that hopefully the Hamming distance thing that we have implemented, we will now be able to take a look at. And before we get into implementing some of the other heuristics, it'll just be a little bit easier in a different representation. So let's go to the puzzle. And in the puzzle, what we're going to do is we're going to change the representation so that the states we're looking at can be expanded more easily. Okay. So let's say that we have a 9 puzzle. In order to track all of the values of each of the cells, we're just going to shove each of them. Is this something that we want to do right now or not? How hard is it going to be to do this later? You know what? I'm not entirely sure about that. In any case, let's go back. Is this something we want to do now? Okay, so ideally what happens at this point is we get to search a lot faster. Where is the value in that? Where is the value in that? So the way that we would go about doing that is we don't need 8 bits for each of these. We only need 4 bits because there's only 9 possible values. And so instead of using 8 bits to store it, we can store 2 cells in 8 bits. And there are 64 bits. So we can do a 4x4 in a long. So we can do a 4x4 in a long. Is that valuable? Is that valuable? The goal check becomes really, really fast, which I think would actually speed this up quite a bit. Because right now the goal check is a giant freaking loop. Okay, yeah, let's talk about just this last part. Well, there's 2 parts. There's copying. This is really expensive because one, we're creating a whole nother instance of the class, and then we're also cloning the bytes for the board. And we could get rid of this one altogether, which would make this faster. And this goal check would literally become a single operation. So I'm gonna say let's go ahead and go this direction. We're going to keep most of this the same. The only thing that we're going to change is the representation of the board from being a byte array to being something else. And we're going to currently limit the size to just being at max of 4x4. So sort of to give you an idea here about what this is going to look like. 1, 2, 3, 4, 5, 6, 7, 8 space. Probably want 2 spaces actually. 2, 3, 4, 5, 6, 7, 8, 9. This is how much memory we're using right now. Each one of these represents one of the bits, because each of these are bytes, right? We have a byte array. And actually this byte array is a multi-dimensional array, which also stores the dimensions of the array and the rank of the array, which is not true in a single dimensional array. So there's even more space being used here. And cloning this has to clone all of those things. Instead, what we're going to do is we're going to just use 1, 2, 3, 4 bits. Whoops. We're going to use 4 bits, which can store up to values 0 to 15, which means that we can handle a 4x4 board at a maximum. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to use a lot fewer bits. Let's go ahead and copy this again and compress it so we get the actual length here. Okay. And then for this one, same idea, compress it, only we don't need all of them. Okay, so you can see here we're using a lot less memory to store the same amount of stuff. Now, to be fair, you can't just have 9 of these. We have to have a long, which is 64 bits. So a lot of this space is going to be unused. But the trick about it is, instead of storing this as an array of bytes, a multi-dimensional array of bytes, instead we're going to store it as just a single long. So let's go ahead and do that. Private long new board. And basically everywhere that we use board, we want to get rid of it and replace it with new board. Initialize. So we want this dot new board equals, and in fact, yeah, call it initialize new board. You know what? Let's go like this. We need a new thing here. I'm just gonna get rid of this altogether. Call this board. And then we're going to call this private long goal. Okay, perfect. Private long goal. Even better. Now what we're going to do is say initialize. And initialize is now a long, so this initialize function needs to return a long. How about generate goal? Instead of, we're going to call this generate goal state. And what we're going to do first is say if n is greater than 16, throw new argument exception. The maximum size this implementation can handle is n equals 4 is 4. Okay. And now we're going to change this to .goal equals initialize goal of n, and then this .state this .board equals this .goal. All right, perfect. All right, hello and welcome to the channel. If you're just lurking, that's totally cool. We're just hanging out on a Friday. I'm implementing the 8 puzzle and using right now breadth first search, and then we're going to switch over to A-star to solve it in just a little bit. Feel free to drop a line, love to chat, say hey, get to meet you, be awesome. All right. What we're currently doing is the way that we were storing the state of the 8 puzzle was kind of expensive, and so now what we're doing is changing the representation under the hood to make it so that it is enormously faster to do some of the common operations in order to improve the states per second dramatically. All right, so we have the goal. We'll come back around to this in a little bit. So we're creating the goal, and then we're initializing the board to the goal state. Okay. Generate goal state. Generate goal state. Now what we want to do is we want to say this is a long result equals 0 long. Is it L? The L suffix is easily confused with the 1. Use capital L. Sure, whatever, 0 long. And then what we're doing is we're saying this one we can just no, we want this to be long value. Okay, this is going to get a little tricky. What we want to do is say that the rightmost bits are going to be 0, 0, and we're going to work backwards. So basically, like of your 64 bits, let's see if we can do this here. This is 1, 2, 3, 4, 5, 6, 7, 8. So this is this right here. And now that we've seen this right here are your 64 bits. We're breaking this up into sections of 4. And each of these little groups is going to represent one value in our array, or excuse me, in our state, and this one is going to represent 0, 0. So let's just pop that in there. So this is going to be 0, 0. This is going to be 0, 1. This is going to be 0, 2, 0, 2. And then this is going to be 1, 0. Is this all making sense? So we're basically going to store them backwards. And the idea behind this is that's just how the math is going to work out. So we're starting at 0, 0. And then each column of the first row is going to be like, first we're going to, let's just make it work. We're going to have result, and equals. So this is a bitwise and that says, no, and we don't want and, we want or equals. And then we want the value shifted left by 4, no, by, okay, size, yeah, by 4. Okay, by 4, no, by the row I times 4 plus no, I times, yeah, this is getting crazy. Okay, I times 4, okay, row bits int row bits equals size times 4 times row bits plus int call bits equals 4. Actually, let's do it like this. Let's do value bits. Value bits equals 4. Row bits equals value bits times size. And then we want j times value bits. Okay, this is complicated, and when it's not entirely clear that all of this needs to go together. And then there's one more step to all of this, which is we want to take all of this and we want to AND it by, oh, we want to, sorry, I want to take the value okay, we're going to call this a u-long. We're going to change all of these. We don't want negatives. U int u int u long value mask equals 0x f. Okay. I will go through and explain all of this in just a moment. I'm trying to keep it straight in my head at the moment. Value bits result equals value and yeah, actually I don't even want the value mask. Okay. I do want this to be a u-long, that is for sure. The result should be a u-long. The value bits is going to be 4. The row bits is the size of the row times the number of bits per value. Okay. And then what we're saying is take the value and then shift it left by the offset for the current cell that we're looking at. And then all we want is value plus plus. And since this is an initialization step, I'm not going to worry about like any optimizations here. I want it to be as readable as possible. I'm not 100% sure that this is correct, but we're going to find out in just a moment. Let's go ahead and say generate goal state. So now we are generate goal state. All right, so we have done this one, we have done this one, we have set the board, we have set the goal. Now what we need to do is anything that touches the board, we need to fix to use the easiest one, to use the new version. Let's do all the easy ones. This is one of the more complicated ones. This is the thing that is supposed to get a lot easier. We don't need this clone anymore at all. We just need the board. We also need the goal equals this dot goal. Control F of board. Generate goal state. I don't want that anymore. And then we're going to come back to that. We're going to come back to that. Is goal. This is now all gone. And this is return is goal equals equals. Nope, not is goal. This dot goal equals equals this dot board. Alright, see how easy that is? So now instead of doing all of that looping, every single state we evaluate, it's just a single like processor operation. And this is going to make it so much faster. Now, let's go back and fix the rest of these. We want to toString it. So now what we want to do is say for, this one's going to be fun. Okay. We want to say var value equals this dot board. And then what we want to do is append this dot board and 0xFFL UL. Wow. Okay. And then we want to say value equals value right shift 4. I need to make this const int value bits equals 4, because we're going to end up using this over and over and over again. We already used it in the initialization. ulong ul ulong ul, and we want to make these ulongs ulong ulong. Okay, great. Still going here. Control F board. We're going to come back to that. That one is done. This is the exact same thing. What it's saying is, give me the value of the board, but only give me, oh no, that's it right there. I want 4. So F in hex notation stands for 15, and that is 4 bits activated, the lowest 4 bits activated, which is exactly what we want. And so this says, give me the lowest 4 bits, and then show them to me like this. Perfect. And then we shift it 4 bits. Oh, I don't want this step board, I want value. Because I don't want to. Okay. And then we're saying shift it, which throws away the smallest 4 bits and keeps the rest of the bits intact. So that should print out correctly. Now, what we're saying is, this dot board, going to say Hamming distance var value equals this dot board. Anytime we want to, we don't want to modify the board, so we're creating copies of it at each state for each operation that we're performing, and then we're going to manipulate the value inside of here. So now we're going to say value and 0xf ul equals, and this is going to be a ulong. So the idea here being that value and the lowest 4 bits equals the expected, and then we increment the expected. But this is also incorrect because this needs to you know what, this is the Hamming distance. We're going to come back to this one because we haven't moved over to A star yet. And I'm not going to worry about that for the time being. Okay, so this is taken care of. This is taken care of. This we're going to do in a little bit. This is taken care of. Return the cost of the action. That's right. We'll come back to that. Okay, this is one of the more tricky ones. What we want is ulong temp equals this dot board. Wait, we want these. And in this case, we want right shift of this dot blank row times this dot times bits, value bits, times this dot in plus this dot blank call times this dot value bits. No, it's not this, it's just value bits. Okay. So again, the idea here is we want to right shift it. Oh, and then we want to take all of this and say and 0x ful. Okay, and this only takes the lowest 4 bits. All right, so now what we have is the value here, and now we want the value ulong of old. Oh, we're going to be able to get even faster than this. But for the sake of argument, for now, we're just going to keep going like this. Okay, so ulong of old, ulong of new, of new equals same idea, only this time we want new blank location dot row and new blank location dot call. What we're doing is, oh, you know what? We actually know the value of the blank location, so we don't need to do this sort of swap. Instead, what we need to do is just put the 0 at the right place. Okay, we can do that. Okay, we can do that. What we want to do, yeah, what we want to do is put the 0 at the right place. So we know that the old, we don't need the value, we need the value of the new location, which is this. Okay, val. We need the value of the new location. We need to put the blank in the new location. We need to put the blank in the new location. Okay, so put the blank in the new location. Every time you get into like bit twiddling, everything gets complicated. Put the blank in the new location. Put the val in the old location. Swap the new old row call. Okay, so we have collected the value. Now we need to put a blank there. Okay, so in order to get a blank, what we're going to do is an AND with everything. We're going to put an AND there. Yeah, we're going to put an AND. Okay. So how do we put an AND? First off, we want to say u long not blank equals 0 x f u l, and we want to left shift this by some amount. And then we want to take the bitwise not of all of this. So what this is going to end up doing is it's creating 4 activated bits, shifting it to the location where we want there to be blanks. Then we're going to swap, we're going to negate all of these bits so all of them are lit up with the exception of those 4, and then we're going to AND that with the board state, and that will leave all of the cells with the exception of those 4 that are already activated, and it will turn off just those 4. Okay, that's exactly what we want to do. So how far left do we want to shift it? It's going to be this sort of a thing. The new blank location. Okay, so we're just going to say int new blank bits new blank offset equals that. Then we're going to say new blank offset, and then we're going to say new blank offset. Okay, and then we're going to say this dot board equals and equals not blank. And in fact, this is so simple, I think we'll just do it like this. Okay, that's good. Okay, so put the blank in the new location. Now put the value in the old location. Okay, so we have the value in the lowest location, and we need to shift it right, and we're going to say this dot board, and this time we're going to OR. There was a blank there before, so we know that all of the bits that we care about are currently set to 0. So we're going to say OR equals val left shift of basically this new blank location, old blank offset. And for this, we're going to say this dot, blank row, this, oh, that was a mistake here, new blank location. New blank location, old blank location. So we're saying give us the value that's at the new place, set the value at the new place to 0, and then add the value to the old place, old blank offset. I want to say that's it. As complicated as that is, once you break it down, it's manageable. That took quite a while. That took almost 20 minutes to do just this one function. That's how that goes sometimes. Okay. So now we have implemented the move, and that takes care of that board. And this is the one where we do want to update the board, which is good. Okay, none of this changes because it doesn't touch the board. Now we need shuffle. None of that touches the board. None of that touches the board. Okay, this initialization does touch the board. And this, again, is not that difficult to do. What we want is okay, this one we're going to do in a little different way. Split dot select. Instead of a byte here, we're going to change these to ulongs. ulong.parse. And then we're going to change them to toArray. And then what we're going to do is we're going to say for each var value in values all right, first we're going to clear the board. This dot board equals 0 ul, and then what we're going to do is we're going to say this dot board equals this dot board left shift left this dot board left shift values dot reverse this dot board left shift value bits. And then we're going to say this dot board or equals value. Yeah, there's one thing we didn't actually do on this initialization, which is to do validate that all expected numbers are present. Okay, so what this should do is it takes all of the values, parses them to ulongs, converts them to an array of ulongs, reverses that, and then starts shoving them back on from the last one to the first because the first one is the lowest value. Yeah, this is going to work. I hope this is going to work. All right, well, that takes care of all the uses of board. This needs to be value bits. Basically, oh, I'm going to sneeze. Value bits. Then want to make sure that we don't use any hard-coded 4s anywhere. Generate goal state value. Actually, you know what? It would be a lot easier to implement this the other way that we just did the last one. We'll come back to that. Really just want to test it and see if it actually works. So really all we want to do is test the goal initialization. Is that right? It's like, I'm going to give it like a, yeah, sort of expected there. Definition of Hamming distance. Ooh, yeah, okay. That. A star. Return plus 0. If that was it, use of unassigned value local variable value bits in puzzle 61. In puzzle 61. Oh. Yeah, I don't need that anymore. Value bits. Because I just made it a constant. $168. 168. Oh, yep. Don't want that. That's a logical operator. I want a binary operator. I want a bitwise operator. Okay, I ended up with a 9 here, so that's bad. And it doesn't appear to have moved anything. So that's bad. Okay. Okay. Let's see. Initialize. 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 Generate goal state. Generate goal state. What we want to do is say value total cells -1. Okay. For int I, nope, u long I equals u long equals max value equals max value I greater than how is it that I'm trying to do this? Oh yeah, because yeah, this is just gonna work. Great. Greater than 0 I minus minus, and then what we want is result and equals value and equals I and 0x FUL. And then down here we want we don't want anything because the 0 is the first thing that needed to get pushed on there. We don't need this value at all either. And this max value can honestly get shoved off to here, which makes this seem a little bit easier. Actually, maybe that is max cell value, max tile value is the size times the size minus 1. And we're just going to shove those on there. And then the highest one is the last one, which needs to be a 0. Let's give that a shot. No, cannot convert type int to ulong. What do you mean? Cannot implicitly. Ulong. Hooray. All zeros. I. Oh, I didn't want and, I want or. $15. Size. This is 3 and 3. I'm really just confused. Program. Hello world. Test initialization. In puzzle 3. Oh, time to debug. What just happened? That's not what I wanted to do at all. .NET Core launch. Configuration. Why is it launching that one and not the one that I'm on? VS Code. Build. BLAS.dll. Oh. That's awesome. That is so awesome. Program. Current working directory. Is it tell it? Oh. Okay. Now we get to look this up. Let's just have it print out a bunch of values. Until I'm not going to sort out the debugger right now since there's only about 20 minutes left. I really just want to get to the point where, I mean, we're clearly not going to get to the end of what we had hoped to accomplish, but I feel like we can get a little closer. So I am just going to print out a bunch of values here, which is console.writeLine of result console.writeLine of I plus I, and then R plus result. Let's see if we can figure that out. Let's go to the terminal. I is 1. How is the result 15? Oh, you know why? Because I am not shifting it. Result equals result value bits. Kind of got close here. Well, that's interesting. So we managed to pull that off, and then we managed to not pull that off. Okay. We want to do this first, and that will create the correct starting point. There we go. Okay, cool. So that got true right there. Now, in the program, we should have shuffled 1. And it did not seem to have moved anything. So let's take a look at that. Shuffle. Basically what shuffle is an indicator of is the move is busted. So move. Move. Now I really want to debug. Let's go ahead and just see if we can get, okay, console.writeLine, new blank offset plus new blank offset. Okay. New blank offset. Old blank offset. Console.writeLine of state board plus this dot board. Now we're going to want to print this out quite a few times. Okay. Console.writeLine of val and val. This is going to tell us whether or not we are collecting the correct place. And then we want to print out the board a few times. We want to print out the board here. We want to print out the board here. And then these were correct in the last implementation, so I'm not super worried about it. So board initial zeroed valed. Let's give that a shot. All right. The old blank offset is 32. Is that correct? There are 1, 2, 3, 4, 5, 6, 7, 8 locations, and there's 4 bits times each of them. That's 32. So that's correct. The board initial. Can we get the board initial in hex? Dot to string x dot to string. I want to say it's just x. I hope it's just x. Not 100% sure on this. Just gonna give it a shot. No. Okay, this is the one thing I am gonna have to do. Fixed point. What was hex? Round trip. Hexadecimal. Ah, X. See, I did have that. Huh. Let's see. Oh, that is actually hex. Now that you look at it. Alright, so what we see here is there is a 0 at the beginning. And then we have, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 0. Now we find the value is 5, which is not correct. Okay, that's not correct. That's what we need to print out. We need to print out the new blank location. New blank location. Console.WriteLine of new blank location. WriteLine, new blank location. One row 1 element 2. 2 times. Alright, so this 16 is incorrect. What it should be returning is 3. 3 times 4 is 12 plus 3 times 4 is 12 plus 2 times, it should be returning 20. So that's crazy. Why is it not returning 20? How is, do I just need parentheses somewhere? I mean, this is all math. This shouldn't, and how is value bits coming out correct? New blank offset. This dot in is 3. Value bits is 4. It's a constant. And this dot new blank location dot row is 1. New blank location dot row. Oh, you know what? I did row twice. Yep. Okay. All right. Now we can get rid of all of these. And keep trying. Okay, we can see it swapped it with the 6 correctly, it swapped it with the 8 correctly. And in each case, it is now telling us true and false for that is the goal or not the goal. So we've handled move, we've handled initialization. Now we just need to make sure that we're handling initialization correctly for the case of this, which should not be that difficult. We're just going to go like this. And I think we're going to put in console.writeLine. Big old divider. Okay. Big old divider. Console.writeLine. Now I want puzzle 3 only. I want to initialize it to this. And we're just going to go like that. And that's that. Let's try that one more time. Yeah, that's the top row, the middle row, the bottom row. Somehow I got it almost entirely backwards. That's the top row. Maybe I just don't need the reverse. That's wild. Why is that happening? The last one that we add in should be the beginning. Maybe I have. Okay. Okay, well, something's still screwed up with the move. And even though I changed the reversing, no, values dot reverse. Oh, I see. That's crazy. Okay. The shuffle. Okay, so there's something wrong with the move still. And I've only got 4 minutes left, so we're just going to put this on this to do, and I'm going to clean this up on my own. Let's see, well, 4 minutes left. Can we get it done in 4 minutes? What could possibly be wrong with the move? So this is 1, 2, 3, 4, 5, 6, 7, 8, 0. So all of the pieces are there correctly. We cleared out the board. Correct. We zeroed out the board. We correctly initialized the board. For some reason, the move now. Let's go add all of that stuff back in. I shouldn't have deleted all of that. Give me the move. Okay. Control C. Control V. Okay. It's at row 2. That's 12 plus 12. is 24, 28. So this is the correct location, and it wants to move it to this location. So we get an 867 254 301 867 254 301. So for some reason it's not zeroing out. It is not zeroing out the value correctly here. It's not zeroing out the value correctly on the last spot. What could cause that to happen? What could cause that? Wait. Value. It's also getting a 0. That's not correct. Okay. It's getting board initial, correct. The value should be the value at the new blank offset. So the new blank offset is 28. This dot board 4, 8, 12, 16, 20, 22, 24, 24. How have I done this wrong? 32. How is 32 ever correct? There are 36. Oh, new blank offset. It wants to swap it with the 3. The new blank offset is 28. Oh wait, move 2, 1. Wait, it wants to move it to its own location? That's not correct. Okay, so expand. Oh, duh. You have to set the blank row and blank call correctly when you initialize. Generate goal state. Nope. Initialize. Okay. If this, no, if value equals 0, what is value? uint 64 ul this. Oh, now I need this. Oh man. 4 int I equals 0, I less than values dot length I plus plus. Values of 1 to 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 1 I. And now I want to say if values of I equals 0, then this dot blank row equals come on. U long value. Yeah, we're just going to go a little long today because I'm going to get this. Equals values of I. Value. The row is value remainder of this dot of n and this dot blank call divided by n equals value remainder in. So if this is 3, this will tell us the row. You cannot apply it to ulong and int. Whatever. 10. How about we add somehow it generated that. Okay. One of these values is going to be 0. Oh, I don't want value. I want I. Come on, man. No, we're still not there. Did it get these backwards? I am doing them backwards. This reverse is no longer correct. Now I want values.length -1 greater than or equal to 0. I minus. One last time. I feel like that's it. 867. Oh man, did we get this? Uh, 867-254-301. 867-254-301. 867-254-031. Perfect. Because it wanted to change it with 2 and 0. Let's try it again, see if we can get it to go somewhere else. We don't need all of those right lines anymore, but yeah, I've sort of learned my lesson about getting rid of them. Okay, this time it moved to the right, 2, 2, and now I want one where it moves up, which is going to be 1, 1. And it did not. And it did not. And it did not. The randomness of this is bothering me. Yes, it did. Okay. Okay. So that's it. We got it to move up. We got it to move left. We got it to move right. All of these are correct. Okay, so quick run now on just the breadth first search solver to see if we did what we hoped to accomplish, which was to greatly improve the speed at which this thing goes. I feel really good about this. We are going to wait 10 seconds, but we're going to see a number bigger than 500,000, I hope. 600,000. All right, so there's still a lot going on, and a lot we're going to have to get sorted out. But it did improve the speed, just not by orders of magnitude. States evaluated. What if we do it in like .NET run C release? All right, we're still doing a lot of copying around, but overall I feel like the move got faster and definitely the check got faster. Oh, there we go. The last one. Okay, so we about doubled the speed. A little bit less than doubled. When running in, oh, well, not quite. When running in, what is this called? What mode is this? Release mode. We're going to wait for one more, and then we're just going to wrap up. Oh, it's just dropping precipitously. So I wonder what's going on there. Certainly, yeah, I would expect. Okay, so this up and down movement, I think, has a little bit to do with the resizing of the array that we're using to store the results. And we had to resize a lot up until we got up to here. But now we're not going fast enough for it to double anymore. And oh, that also went long for some crazy reason. Interesting. Anyway, all right, point being, we did a good job. We have actually increased it. I think if we were to average these out, like, well, this is doing total all time. So it's going fast and it's going slow, and then fast and then slow. And over time this number is going to even out if we let it run long enough. But so we did not really accomplish the goal here, which was to increase it by orders of magnitude. We'll pull out a profiler next time around and we'll see what's going on, just to make sure that we are doing it correctly, you know, and where things are getting hung up. And then when we're done profiling, hopefully we'll be able to go significantly faster. All right, did not accomplish the goal today of actually solving the 8 puzzle, the hardest one, but that's just how it goes. We'll be back. We'll try again next week. Thanks everybody for joining, and we'll see you later.